I know, that's what I'm thinking.
How long have you been using that? Once again, this
human watching after that and when she killed her. Like I have okay. I'm gonna wear that. I get interested. So,
yeah, so you say I mean, did you go to yeah, it's gonna be that like. She's never gone. And then. Oh, that's right, yeah. Okay, how you guys should do exam? Yeah. Oh, yeah.
Okay, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Doing good. Our weather's been crazy. It feels like it goes from raining to sunny like within within a few minutes. And so yeah, hopefully it starts to settle down after a bit. Okay, so plan for today, we have a little bit left to finish on the lecture notes on differential vector calculus. So we're going to talk about the curl today. We're going to talk about what that means, how to compute it, and kind of what that means physically for engineering systems. And then we're going to move on to integral calculus from there. So we're taking kind of a quick tour of multivariable calculus. We're going to talk about today about parameterizing a curve, what that means, computing line integrals, and then hopefully by the end we'll get up to a Green's theorem, which is a very important theorem for applied math in physics. Okay. All right. So if you haven't had a chance to pick up your midterm, I brought them again today. I'll probably bring them one more time on Tuesday if you haven't had a chance to pick it up then. But if you don't come get it by Tuesday, I'll still have it. It'll be in my office, but you have to come to my office to pick it up. Right. So today, Tuesday, and then come to my office. Okay. Homework 4 is posted. It's all about this vector calculus stuff. I think it's not due for a bit just because we still have quite a bit to cover in terms of this stuff, but I would definitely take a look and get started if you have any questions. Okay. All right, any questions I can answer before we get started for today? Okay, all right, so let's go ahead and get started. So let's start today by talking about the curl of a vector field. Okay, so we are doing kind of a very quick tour of all of these kind of important vector calculus operations. So last time we went over the gradient, we spent quite a bit of time talking about that. We talked about the divergence, what that means. So kind of the last kind of operator that we have to cover before we move on to the integral stuff is the curl. Okay. Okay. So to kind of motivate the curl, let's talk about kind of what a vector field represents again. So let's kind of review that. Right. So a vector field is basically a function where at every point, at every physical point in space, we have assigned a vector value. So this entire unit here is all about kind of multivariable functions. And so functions that have multiple variables. Usually our multiple variables are going to be basically physical coordinates. So X and Y, sometimes X, Y, Z. Okay. So a vector field is a multivariable function where at every point in space, we have a vector quantity. And so I think we drew an image of this last time. Then we kind of draw another one here. Okay. So we have our physical domain here. This is just a two-dimensional space, so we just have two variables, X and Y. Okay. A vector field is going to be one where at every location in this space, we're going to have a vector. So remember, a vector has two quantities to it. So it has both magnitude and direction. So it might look something like this. And so the vectors might change. In fact, it is very common for them to change at different locations. Okay. So I'm not gonna fill this entire area with arrows, but but you'll start to get the gist of it, right? So each of those arrows there represents a different location, X, Y, in the in the space there. And at each location, we have a different vector value. Right, so mathematically, the way that we represent this is that we usually give it the symbol V with kind of the arrow on top for vector field. And in this case, this vector field is a function of X and Y, right? And what we can say is that each this vector function V has both an X component and a Y component, and each of those components, the X component and the Y component, are functions of X and Y. Right? So it usually looks something like this: Vx of X comma Y, and Vy of X comma Y. So that's what it means to be a vector field. So, vector field, vector value, just think of it as, we have a vector value component at each location, X and Y, okay? Now, the reason I'm reviewing this is that, if you look at this vector field right here, there's a lot that can be said about kind of the pattern of arrows or the pattern of vectors that we have showing up here, okay? And so if you kind of trace out the path, right? So if you kind of follow a path right here, you can see that, a lot of times these vector fields have really interesting curvature associated with them. So the path tends to curve if you follow the vectors in that field. Okay? Okay. And oftentimes, quantifying that curvature or quantifying how much, your path is going to change directions within a vector field, that's something that's a very of engineering significance. Oftentimes, that's something that we want to compute from these vector fields, right? So, for example, a lot of times we use vector fields to represent the velocity field of a fluid, right? So if you have airflow that's going over an airplane or airflow that's going past a car, oftentimes you want to use a vector field to describe, the path of air going over that system. And oftentimes you want to see how much, that air is going to swirl. So if you've taken fluid mechanics before, you've probably heard of the term like a vortex or vorticity, and those are often associated with curvatures within the velocity field of the fluid flow. Okay, so how do we do this? And so mathematically, the way that we kind of quantify this curvature is by taking the curl of the vector field. Okay? So the curl is a derivative operation. So we're going to be taking derivatives, right? And the way that we compute it is like the following. So let's say that we have a vector field V, okay? Just like we have up there. Now this V may have 3 dimensions. And the way that we compute the curl is we take our nabla, and so kind of our derivative operator that we've been kind of working with since Tuesday. And we take the cross product between that nabla and this vector V. Okay. So this right here is kind of the symbol for the curl of a vector, right? So it's nabla cross V. So mathematically, the way that we compute this, if we kind of think back to kind of before the midterm and how we compute cross products, we use this kind of 3x3 matrix, right? And we want to take the determinant of this matrix. Okay, so we have I, J, K in the first row. Second row, we're going to have the components of our nabla, which is all the partial derivatives. We have partial x, partial y, partial z. Okay. Now for this curl here, I'm taking a three-dimensional example. Usually, you can take the curl in 2 dimensions. That's usually fine, but the full expression is in 3D. Okay. And then on the last row, we have the vector components of the vector field V. So we have Vx, Vy, and Vz. Okay. All right, and so to take this curl, you're simply just going to take the determinant of this matrix, just like you would with the cross product. Okay. Okay. So I'm going to write up the exact formula expression for you here, but for me personally, I find it a bit easier to remember just this matrix, just because it has kind of a nice structure. But if you prefer to remember the formula, that's fine too. Okay. All right. So the formula for this, we'll go component by component. So we have the x component first. So we have partial Vz, partial y, minus partial Vy, partial z. Okay. And that's the x component. Okay, so that's multiplied by I hat, minus partial Vz, partial x, minus partial Vx, partial z. That is the y component. And then the z component, we have partial Vz, or partial Vy, excuse me, partial x, minus partial Vx, partial y. And that's the k component, or the z component. Okay, so the curl is a little bit cumbersome to compute just because there's a lot of partial derivatives. But what you can see here is that when you take the curl of a vector field, you actually get another vector, right? That's the whole point of taking a cross product, is you get a vector. Okay. So the result of a curl is another vector, and the direction of that vector is very important because the direction of that vector tells you, the axis in which you're rotating. Okay. So I think this is kind of most obvious if you take the curl in 2 dimensions. And so if you take the curl in 2 dimensions, then your curl is going to point in the z direction. And that makes sense because if your flow is 2-dimensional, you can only rotate around the z axis. Okay, so next thing we're going to do is we're going to do an example just to see how this is computed. But any questions on the curl here? Okay. All right, so let's do an example to see how this is computed. Okay, so let's define a vector field V. So we'll say let V equal by Z, 3ZX, and Z. Okay. So those are our 3 components of the vector field. So you can see the first component here, this is going to be Vx. Second component here, the 3ZX, this is going to be Vy. And the third component, which is Z, that's going to be our VZ. Okay. So let's take this and let's compute the curl. Okay, so to compute this curl, you can just plug into the expression that I have there, but let me show you kind of how I kind of mentally do it in my head with the matrix. Okay. Okay, so to compute the curl, let's go ahead and plug it into our 3x3 matrix here. Okay, so we have the curl of V. So this is I hat, J hat, K hat. Second row, we have all the partial derivatives. So we have partial x, partial y, partial z. And then in the last row, we have all of the components of v. So we have yz, 3zx, and z. We've kind of made up this kind of 3x3 matrix here just for the sake of taking its determinant. Okay, and so evaluating this determinant, let's go ahead and do that. So we have partial, oops. We have a partial y of the function z, okay? So remember, to take the determinant of a 3x3 matrix, you kind of, start with by kind of crossing out the first row and first column, and you take the determinant of this 2x2 matrix here. Okay. So you have partial y of the function z minus partial z of the function 3zx. Okay. And that is the x component I have. Next, we're going to take the middle component here. So we're going to cross out the first row and the second column. And then we're going to take the 2x2 determinant of whatever's left. And so this is going to be partial x of the function z minus partial z of the function yz. Okay. J hat. And then we have the final component here, where we cross out the first row and the third column. And then we just take the 2x2 determinant of whatever is left here. So we have partial x of 3zx minus partial y of yz. Okay. Okay, so let's go ahead and evaluate all of these partial derivatives here. So remember, when you're taking the partial derivative, all the other variables are treated as constants, right? And so first we have partial y of the function z. So this is just going to be 0 because there's nothing in that expression that's a function of y. Next, we have partial z of 3zx. Here we have a z. And so this entire expression here becomes a 3x. After taking the derivative with respect to z. Next, we have partial x of the function z. This is not a function of x, and so that's just going to go away. Next, we have partial z of yz, and so the z is going to go away, and then we end up with just y. And then for the last component there, we have partial x of 3zx. This is just going to be 3z. And then we have partial y of yz. This becomes just z. Okay. All right, and so if we put all this together, we simplify it, then our curl is equal to, so we have nabla cross v is equal to, we have a minus 3x. That's our x component. Our y component here is minus positive y, excuse me. So we have minus. So you have positive y here. And then in the last component, we have 3z minus z. And so that simplifies there to 2z. Okay. Any questions on how we took the curl in this example? Yes.
So since it's I minus chicken plus K.
Yeah.
How come being Y plus the bottom coordinate Y is negative?
Because we have two minuses here. So we have this minus sign. So that first minus sign just comes as a consequence from the cross product. And then we have this minus sign kind of on the inside here. So the two minus signs. Yeah. Yes.
You want us to show us that form? We be like I had.
You can keep it I hat, J hat, K hat form. Yeah, whatever is most fun. Any other questions on this? Okay, good. All right, so that's the curl. So let's talk about kind of its physical intuition a little bit more. Specifically, let's look at a case for when the curl is 0. So it is possible for the curl of a vector field to become 0. So when the curl is 0, this basically means that we have an irrotational vector field. Now, if you get into fluid mechanics, especially if you go into aerodynamics, aerospace, and this is a term that you're going to hear quite a lot. But it's a little bit kind of hard to interpret, right? So what we just computed in the curl is actually a very local quantity. And so if you can kind of look at the result that we have here, right? This curl is you, in order to fully evaluate this curl, you have to evaluate it at a particular location, X, Y, Z. Okay. So it's important to note that the curl can actually change, depending on where you are in the vector field. But if you look at this result here, there is a location where the curl is actually equal to 0, right? And so if you evaluate this curl at the origin, then you would have 0, 0, 0. Okay. So what that means is that if your vector field is irrotational at that location, then there's going to be no local spinning. I should say rotation that occurs. Spinning is a little bit casual. Okay. So the way I like to visualize this is that, if your curl is 0 at a particular location, if you were to stand at that location, if you were to kind of sit there, or if you don't want to get, put yourself in that position, you can put a stick there, right? And so that means that if you put a stick at the location where the curl is 0, then that stick will not change orientation. That's how I kind of like to think about the curl. Right? When I think of crow, there's this kind of species of seals. This is a little bit of a tangent, but I think these seals are really cute. They're called round ring seals, and they like to kind of sit in the water. They just kind of like to spin. So I think of those seals whenever I think of irrotational and curl. So if there is a curl at a location, then the seal will spin at that location. Okay. Now it's possible for a vector field to be irrotational everywhere, right? And so it's possible for a vector field so that everywhere there's no curl at all. Okay. And if you kind of keep up this analogy where the vector field represents a fluid flow field, that means you can travel along an irrotational fluid flow field, and you'll never change orientation. You'll just kind of stay in the same place, or stay in the same orientation. Okay. So for example, let's say that we have a vector field that looks something like this. Okay. And let's say that this vector field here is irrotation. Okay, so if this vector field were irrotational, and let's say that we have an object that's kind of traveling along this vector field, so it's following this line, right? And so let's say that we start an object right here, and it has this orientation just like that. Okay. So as it translates along the vector field, that orientation is not going to change. It's going to stay the same orientation. So orientation does not change for an irrotational vector field. Okay. So irrotational vector fields are really interesting just because it's always very fascinating to see, because even for flow fields with some curvature to it, it is possible for some of those to have no curl at all. And so you could be your entire body might be kind of rotating around a certain point, but the orientation of your body may not change at all. All right, any questions on this? Okay. All right, so that is the curl. And so let's go ahead and move on to kind of the next topic here. Okay. So now that we All right, hello. Okay, good. Okay, so now that we've gone over all of the components of vector integral of this differential calculus, right? Okay. So far we've covered the following operators. We've done the gradient. We've done divergence. And we've done curl, which is what we just did. Okay. Okay, so all of these operators, I would consider them to be derivative operators. So, they involve taking the derivative of a scalar field in some way. So they involve partial derivatives and vectors and so on and so forth. Okay. So these operators here kind of form the backbone for a lot of what we do in kind of multivariable calculus, as probably you've seen in your previous classes before, okay? There are relationships between these operators for certain situations, but those also involve integrals as well, okay? So that's kind of the next kind of big topic that we're going to cover in this unit here, which is, integral vector calculus. Okay, so integral vector calculus is this is a very important topic because a lot of theories and a lot of very important kind of theorems and concepts in physics and applied math and engineering, they're kind of built on these kind of theorems. Okay. So you've probably seen some of these theorems before in your previous classes. It's just that probably they've gone over them kind of very quickly, and so my goal with this unit here is to kind of reintroduce these theorems to you. Hopefully you've seen some of these before, but also to kind of tell you a bit more, I guess, context in terms of an engineering environment. Okay. So the first one that we're going to go over that I hope we'll have enough time for today is Green's theorem. Okay. The second one that we're going to go over probably on Tuesday is called divergence theorem. Sometimes the divergence theorem is credited to Gauss, and so sometimes we call it Gauss's theorem. So those first two are really interesting because they show you kind of their equivalence relationships, and so they're kind of a way to transform one type of integral into another type of integral, which is useful because oftentimes one type of integral is easier to compute than the other. Okay, so I call these two theorems often the integral transform theorems. Because we're going to be using them to transform between two different types of integrals. Okay. Now the third theorem, I don't know if we're going to have enough time for it. It's going to depend on where we are after Tuesday. But the third theorem is called Stokes' theorem. But we'll only get to that if it's time for me. But the two that I really want to go over, just because they have a lot of applications, are Green's theorem and divergence theorem. Okay. Okay. So the reason these theorems are really important is because a lot of theory in applied math and science is formulated in terms of integrals, right? In particular, where you're going to see these integrals a lot is in the application of conservation laws within applied math and science and engineering. So conservation laws kind of form the backbone for a lot of our theories: conservation of mass, conservation of momentum, conservation of angular momentum, conservation of energy, right? So all of those conservation laws are off in their kind of pure form, are often expressed as integrals. And oftentimes, based on the integral theories, there's often a lot of really fun, cool things that you can actually do with it, like the development of computational techniques like finite element analysis, finite volume analysis. Those are often based off these integrals. So being able to transform integrals from one form to the other, especially multi-dimensional integrals, 2D, 3D integrals, is really helpful and really important for these to work. Okay. Okay, so that's kind of the idea, or that's kind of the motivation for doing this. So let's start working towards Green's theorem. Okay. So Green's theorem. Green's theorem is a relationship between a double integral and a line integral. Okay. So basically, it's going to look something like this. I'm going to leave it kind of arbitrary for now, just as we develop the theory. But eventually, it's going to look something like this, where you have double integral across some area A. Okay. And there's something that's going to go in this integrand here. Okay. This is going to be equal to a line integral. Okay. Specifically, a closed line integral, okay, around the boundary of A ds. Okay. So Green's theory Green's theorem is going to allow us to form this kind of relationship between these two types of integrals. Okay. And this is useful because usually one of these integrals is going to be a lot easier to compute than the other. And so if you're ever in a situation where you have to compute one of these integrals, you can use Green's theorem to transform the integral into the other form and do the calculation that. Okay. Usually these theorems are not introduced that way because usually they're introduced as as part of the conservation laws. But that's usually how they're kind of used in practice, especially within the development of computational techniques like finite elements, finite volumes. And so these theorems are kind of a tool of convenience. Okay. Okay, so that's where we're going. But of course, in order to get to this point, we have to better understand, the integrals that are involved. Okay, double integrals, I think we're kind of more or less straightforward. We're not going to spend too much time on that. But I did want to spend some time reviewing line integrals. I think those are a little bit, a little bit more mysterious. Okay, so let's take a moment to kind of go over what a line integral is and how we actually. Okay. Okay. So to start out our discussion with line integrals, we need to talk about what it means for a curve to be parameterized. Okay. And so a parameterized curve, what that does is that traces out a path in space, so in 2D space or 3D space, using one variable. So a parameterized curve is nothing more than just a parameterized vector, right? Where each component of the vector describes a certain location in space, and those components depend on one independent variable, okay? All right, so mathematically it looks something like this. And so usually for parameterized curves, we use the variable t, just because t is usually denotes time, and that time there kind of denotes kind of the x, y, and z components of where that location is, or where you are in that path at that time t. Okay, and so what we say is that we have r of t is equal to x of t, y of t, and z of t. Okay, where each of these components describe the x location, y location, and z location at a particular time t. Okay. So in this case, t is our parameter. T, that's our parameter of our parameterized curve. And then we have each of the components x, y, z that describe this location at that time t. Okay. Okay. So let's do a very kind of simple example of a parameterized curve. And so let's parameterize the path around a circle. Okay, so let me draw a circle in XY space. Right, so we have our coordinates x and y, and so our circle kind of looks something like this. Okay. Imagine it's a perfect circle. I remember my geometry teacher in high school was very proud because he could always draw a perfect circle on the whiteboard. He says it's all in the hips, so he kind of gets his whole body into it. I can't do that here, obviously, just because I'm on iPad. So all my circles look like an egg, but just imagine that it's a perfect circle. Okay. So on this circle, we are going to travel around. And so let's say that we're going to take a counterclockwise path around the circle here. Okay. Okay, so the parameterized curve for this circle here, so we'll say it's r of t. Okay. Let's say that this is equal to 2 cosine of t, comma 2 sine of t, comma 0. Okay. It's a two-dimensional curve, but I'm going to put the z component there just for completeness. But we'll say the z component there is 0. Okay. Okay, so at any time t, this r of t function here tells us our coordinates are where we are on that circle. Okay. So for instance, let's see where we are at t is equal to 0. Okay. And so we're going to compute r of 0. Okay. And so at t is equal to 0, let's plug in and let's see where we are. So our x component there is going to be 2 times cosine of 0. Cosine of 0 is just 1. And so our x component here is going to be 2. Okay. Our y component, we have 2 sine of t. So we plug in t is equal to 0. Sine of 0 is just 0. Okay. And so our y component is going to be 0. And our z component still going to be 0, because 0 at time 0 is 0. 0 at any time is 0. Okay. So that means our physical coordinate at time is equal to 0 is going to be 2, 0, 0. And so where that is on the curve here, that's right on the x-axis here. So this is our location at t is equal to 0. Okay. Now t is equal to 0, that's usually your starting point. And so what we said that our starting point on the circle is going to be at t is equal to 0. Okay. Okay. Let's evaluate another location on the circle. So let's say that we're going to evaluate this at pi over, we'll make it easy. We'll make it pi over 2. Okay. So our time has kind of advanced forward a little bit. So we've gone up to time is equal to, what is that? That's 1.57 something, whatever pi over 2 is. Okay. So if we evaluate our parametrized curve here, so we have r pi over 2, right? Let's evaluate each of the components at that time. So first we have 2 times cosine of t. So cosine of pi over 2, cosine of pi over 2 is 0. Okay. Next we have 2 sine of t. So we're going to evaluate sine of pi over 2. Sine of pi over 2 is 1. And then 1 times 2 is 2. Okay. And then 0 is still 0. Okay. And so after time has advanced by a little bit, we've moved to this location on the circle right here. So this right here is our location at t is equal to pi over 2. Okay. And you can evaluate this at all other intermediate times as well. So what you're going to see is that we're going to follow the circle around this path. Okay. So that's kind of the idea of a parametrized curve. And so a parametrized curve, you're in 2D, you're technically in 2D space, 3D space, but the parametrized curve will kind of detail a certain path. And so, it's literally, you're in 2-dimensional space and you're walking on the path, and the curve kind of describes where you are on that path at any time. Okay. All right, any questions on this? Okay, good. Okay. So parametrized curves are interesting because it takes kind of a 2-dimensional concept of a location and you kind of turn it into a 1-dimensional function, right? Now you can take your parametrized curve and you can compute its tangent. Okay? So the tangent is nothing more than just a vector that points, parallel to the curve at a given point. Okay. So this is pretty straightforward. So, to compute the tangent of any curve, you're just going to simply take its derivative. And so the same is true here. So we're going to take the derivative of the curve with respect to the parameter. So in this case, which is t. And so the tangent is just simply dr dt. Okay. And so you're just going to take the derivative of each of the components. So we have dx dt, dy dt, and dz dt. All right, and then this is going to give you a vector which points kind of, tangent to the curve. Okay. So that's an important part because that's that gives you kind of the direction. This basically gives you the direction of the path at that particular location. Okay, so now that we've talked about parameterized curves as well as this tangent, we're now ready to kind of introduce a line integral. Okay. So a line integral, it's technically a one-dimensional integral. So you're not taking multiple integrals, but a line integral is a one-dimensional integral in multi-dimensional space, which is kind of a weird concept to kind of wrap your head around. All right, because now that we have these parameterized curves, our parameterized curves gives us a way to kind of travel in a particular path in multi-dimensional space according to a single variable. Okay, so a line integral is a you can think of it as almost like an abstraction or a generalization of a regular integral. But the idea with line integrals is that you're kind of integrating over an arbitrary path in multi-dimensional space of a multivariable function. Okay. Because usually, when you have a multivariable function, so a function of multiple x, y, z variables, there's this notion that you have to integrate over each dimension individually, right? So that gives rise to our typical kind of double integral, triple integral, because we have to integrate each variable, right? So if you're in 2D space, you have a double integral, one integral over x, another integral over y. Okay. A line integral lets you integrate a function along a specific path so that you just do one integral. Okay. Let me kind of illustrate this for you, because I think it doesn't really make a lot of sense until you illustrate. Okay. So if we look at a regular integral, so a regular integral, let's say we're integrating a function between 2 points A and B. Okay. And our function is only of one variable, x and of x, and we're integrating between x is equal to A and x is equal to B. Okay. Okay, so what this looks like, right? So let's say we have 2 points here, A and B. Okay. Right. When you do a regular integral, you can think of it as you're integrating the function between these 2 points right here along that path, right? And so the path that you're taking is simply just along the x-axis. Okay. And so if you were to kind of draw it out, you basically be integrating along this path right here. Usually we don't think of it in this terms, because usually we're focused on just the function itself. But if you look at the path, it's really just a horizontal path along the x-axis from A to B. Okay. For a line integral, so a line integral might look something like this. It's a party going on out there. Okay. So a line integral, might look something like this. Okay. So again, maybe we are kind of integrating between 2 points A and B, But now this A and B kind of has an abstracted kind of meaning. So maybe this A and B now, instead of being just locations on the x-axis, these A and B are just arbitrary points in two-dimensional space. Okay. Right, so visually it may look something like this. Right, so once again we have our XY axis. Maybe now our location A is something right here. Okay. And our location B is up here. Okay. And now our path, instead of just being a flat path along the x-axis, maybe now we take kind of an interesting path between A and B. Maybe that looks something like that. Okay. Where that path is a parameterized path, parameterized according to our variable t. Okay. All right, and of course, our function f here will take different values as we kind of go along that path. Okay. So the line integral is really meant to be just kind of an abstraction of our typical 1D integral, where instead of doing just a regular flat kind of horizontal path, we're taking kind of a little crazy path, you know, in two-dimensional or even three-dimensional space. Okay. Okay. Any questions on this? All right. So let's see how this is actually done, or how this is actually computed. Okay. Because this expression here that I drew for the line integral can be a little bit mysterious. And I know that, you know, when I was in college, when I was a student, you know, I would look at an expression like this and my eyes would just kind of glaze over because, you know, it was like too much math to handle at one point. Okay. So let's go through each component here, or each part of this, and talk about how it's actually done. Okay. All right, so let's start with the most important part. So let's start with f of r. Okay. Okay. So this f here represents our integrand, right? So it's the function that we ultimately want to integrate. Okay. And what f is a vector field. So we have a multivariable function f here, that's vector value. So every location f is going to have an x and y component, kind of like we started our discussion with today. Okay, so that means technically f, we can write it like this. So there's going to be fx, which is going to be a function of x and y, and an fy, which is also going to be a function of x and y. Okay. Where fx and fy, those are the x and y components of the vector field, evaluated at each location x and y. Okay. So that's f, but what's f of r, right? So r, right? We just talked about r. So r here, that is our parametrized curve, or that's the path along which we want to perform our integral. Okay. And of course, it's expressed as a parameterized curve. Okay, so that means our R. Okay. Since our R here is a parameterized curve, that means it's going to be a function of our parameter T, right? Our R is also going to have its components. So R is going to have an X of T and a Y of T. We'll assume it's just two-dimensional. So we'll assume that there's no Z of T at this time. Okay. Okay. So what does it mean to combine these two ideas? And so what does it mean to take F of R? Well, what that basically means is that, we're going to take our vector field F and we're going to put it, or we're going to parameterize it in terms of our parameterized curve. Okay. So in order to perform the line integral, okay, in order to perform the line integral, we have to express our vector field F in terms of our parameterized, or in terms of the parameter of our parameterized curve. Okay. And so to do so is actually very easy. So basically, our parameterized curve has an X and Y component, right? So basically, all we have to do is that whenever we see X and Y or Z in our vector field, we just plug in that component of the path, right? And so for X here, we have that. And so Y here, we're going to plug in there. X, we're going to plug in there. And Y, we're going to plug in right there. Okay. Okay. So that sounds kind of confusing, but I think once we kind of do an example, I think it'll all be kind of clear. And I kind of wanted to finish up today with that example, just to kind of put a bow on this topic. But any questions on this before we do that example here? Yeah.
Did we assume the R sub T is the gradient?
No, well, the not quite. Yeah, so we'll bring the gradient back in once we get to greens. Yeah, so this is kind of something set. Okay, so let's do an example. Just so you can kind of see it all together, because that was all kind of just generic kind of conceptual math speak. So I think it's good to kind of put this together. Okay. Okay. So let's compute this line integral. Okay. So our line integral is going to be integral from t is equal to 0 to t is equal to 2 pi. Okay. Of our vector field F of R. And we're going to take the dot product between that and the tangent of our curve dr dt. Okay. So remember this dr dt, this represents the tangent of our parameterized curve. Where our F, our vector field, looks like the following. So our vector field has three components, and so we're going to do a three-dimensional case here. Okay. So our vector field is going to be Z for the X component, X for the Y component, and Y for the Z component. I know it's a little confusing, but I wanted to kind of keep the mathematics simple for this one. Okay. And our path here is going to be an upwards helix, and so it's a path that's going to be circular, but we're going to progress upwards at a linear rate. Okay. So our R of t is going to be equal to cosine of t, sine of t, and the z component will be 3t. Okay. So this path right here represents an upward helix. And so if you were to kind of plot this out. Okay. Right, so we have a three-dimensional axis here. Okay. And so an upward helix is going to be one where, you know, we kind of go upwards like this. Okay. So, you know, eventually, you know, as time progresses, our z component is going to increase at a rate of 3t. And at the same time, we're going to rotate around the z-axis due to the cosine and sine. Okay, so we're going to be integrating our vector field f along this kind of helical. Okay. Okay. All right, so let's go ahead and get started with this. So to compute a line integral, there's a couple, you have to kind of evaluate both components of the integrand here. So let's start with f of r. Okay. So let's start by parametrizing our vector field in terms of our path. Okay. And so to do that, we're just going to plug in the specific components into each part of the vector field. Okay. Okay. So let's look at our path again. So our path here is cosine of t, comma sine of t, comma 3t, right? And so cosine of t here, that's going to be our x of t. Our sine of t here, that's going to be our y of t. And our 3t, that's going to be our z of t. Okay. So let's plug those into each of the kind of expressions in our f, right? So our f, let me write it again down here, is equal to z, x, and y. Okay. So if we plug in the corresponding, components of our path, our f of r here, right? First, we're going to plug in z of t. So z of t is going to be 3t. Okay. Then we're going to plug in x of t. X of t here is cosine of t. And y of t here is sine of t. Okay. Okay, so all I did here was I plugged in the components of our path into the appropriate locations in our vector field. All right, any questions on this part here? Yeah. Oh, yeah, for sure. Yeah, so for this part right here, the vector field that was given to us in the problem is this one right here, right? So our f is z, comma x, comma y, right? And so to parameterize the vector field in terms of our path, you're just going to plug in each component into the path according to the variables in our vector field. And so basically, for z here, we're going to plug in our z of t from our path, just like that. And then for x, we're going to plug in the x component for our path. And then for y, we're going to plug in the y component of our path right there. So basically, everywhere you see x, y, and z in the vector field, you're going to plug in that component from the path. Any other questions on this part here? Okay. All right, so that's step one. Step two, now that we've parameterized our path right here, let's go ahead and compute our tangent. So our tangent is going to be dr dt. Okay. So in this case, we're going to take basically dx dt dy dt, and dz dt. Okay. So each component of the path, we're just going to take the derivative with respect to t. Okay. Okay. So let me write out our path again. So our path r of t is cosine of t, sine of t, and 3t. Okay. So we're just simply going to take the derivative of each of those components, and that's going to be our tangent. Okay. So first we have dx dt. So dx dt is the derivative cosine of t. So that's minus sine of t. Then we have the derivative of sine of t, and so that's going to be cosine of t. And then we have the derivative of 3t, which is just 3. Okay. So computing the tangent is pretty simple. You just take your path and you just take the derivative of each component there. Okay. Last step before we actually integrate is to compute the dot product between these two quantities. So the dot product, we have f of r dot product with the tangent. Okay. So we're going to take the two vectors that we just computed in part 1 and part 2 and just take their dot product. Okay. So that's going to give us a scalar quantity. Okay. We have dot product between this and this. Okay. So their dot product, we're just going to go component by component. We have a minus 3t sine of t plus cosine squared of t plus 3 sine of t. Okay. All right. So this part's pretty straightforward. Just take, you have two vector quantities there. You just take their dot product. Okay. All right. So after you take the dot product there, last step is just going to be to take its integral. Okay. And so our integral in this case, we have an integral from t is equal to 0 to t is equal to 2 pi. And our integrand is exactly that, that dot product that we have above. So we have integral of minus 3t sine of t plus cosine squared of t plus 3 sine of t dt. Okay. And so through all that operation there, we have just a simple one-dimensional integral here. It's not the easiest integral to do, so there's a little bit of integration by parts here and maybe some trig identities to kind of help you out. But if you evaluate all those integrals, what you're going to get is 7 pi. Okay. So that's the idea of a line integral. So a line integral is eventually you're going to get a line integral down to just a one-dimensional integral like this, but it's an integral along an arbitrary path. So you have to factor that into your calculations. Okay. Any questions before we wrap it up for today? Okay. All right. So that's all we got time for today. If you haven't had a chance to pick up your exam yet, I do have them up here. So you can come pick it up. If not, thank you guys for coming today. I hope you guys have a good weekend, and I will see you guys on Tuesday.
Yeah, I got it.
I did. Afterwards. Church library. Service on the. Oh, no. Super. Oh, there's a thing.
I swear. It's like what sucks is like it's the education. A lot of it is like